Thanks everyone. On behalf of Imagination, we're very excited to be here. CASPA is a very large part of what we want to be working with the community going forward, and there's a lot of interest doing more and more together, so we're very proud to be presenting at this conference. Well, I guess two tough acts to follow. I was a little worried about following Michael also, and then Raja was hoping, here's an engineering guy and it'll be okay, and then he pulled out that video. And I thought, wow, now I have another tough act to follow. So we're going to talk a little bit about virtualization in home sensor networks, and we'll tee it up by talking a little bit about IoT and a little bit about what's happening in Internet of Technology devices. I think none of us truly knows the impact of IoT. It's so early on. Lots of opinions, what it's going to mean to us, how it's going to change our lives. If we look back a little bit, it's hard to imagine, it's hard for our kids to imagine a world without cell phones, a world without the internet. Years ago we would have heated debates about issues and facts and figures from history, where now our kids can look up the same information in 3 to 5 seconds on the internet. So it's hard for them to imagine a world like that. Just as the next generation, those born today and in the next 10 years, will not be able to imagine a world without IoT, without machine-to-machine connectivity, without all those little sensors that are going to be literally surrounding us. They won't have any idea what the world was like before that. So how big is the market? Well, we've seen some numbers already. It's certainly billions or tens of billions. And I think that there's an incredible amount of money at stake. Cisco did a great job of highlighting where money will be made and potential revenue from it. And I think, from my perspective, I think that it will become much larger than people are imagining if you look out in time. And why is that? Well, there's a number of contributing factors here. One is sensors themselves are becoming much smaller. If you look here at all the connectivity you can get in a sensor, really a computer the size of a grain of salt, 1 millimeter by 1 millimeter by 1 millimeter cubed, can give you all the functionality here. And you can read through it, I won't go. But connectivity, antennas, battery capability, processing power, and that kind of size already today. And then if you go to the size of a speck of dust, you can still do amazing things. Temperature measurement, pressure measurement, those kinds of things. And then in the picture to the right is a much more high-functioning sensor. So sensors are not only getting incredibly small, but they're also getting very power efficient. And the sensor innovation is one piece of what's going to help enable this. So what are some of the smart sensor trends? Well, clearly single function to multifunction, much more interactive. This idea of input, output, turning on and off, obviously is going to be much more interactive, voice activated, all those kinds of things. A lot of the things we take for granted manually become automated, and there's lots of examples of that. And the other piece that is obviously power becomes more important. We have to look deeper and deeper at system power constraints instead of component power constraints, and I've got an example that shows why that is. Also, these sensors are capable of transmitting a lot of information, and so, in essence, as they get smarter, they need to get smarter also about filtering this information. You can't keep sending it on and on into the network, because you'll see in a moment what happens when you do that. So this is a system power example one of the large chip companies put out into an application note. It's a BTLE example for the engineers in the room. This is, the spikes here is current spikes, and so if you take the area under the curve, you get power. So what's happening here? Well, we're in idle, we're sleeping, and then all of a sudden the CPU wakes up, it initializes, it loads some registers, it gets ready to receive and transmit information. Then look at the spike on the receive side. So there's a little bit of area under that curve. And then it waits, and then it transmits, and then it continues to process, probably storing information in memory, etc. So what's the interesting piece of this now is that the transmission portion of the total power is not the dominant piece, as you might imagine. So as the CPU is processing and waking up, it's using a lot of power. And so what can you do now to lower power? Well, if you control enough pieces at the system level, you can turn on more efficiently. You can decide what you're going to save. Maybe you're filtering some of the information, you're not saving all of it to memory. Maybe and then you can squeeze in the time factor you hear, in this case the processing time factor, by making it much more efficient. You can save a lot on system power. Okay, the internet cow. So this is a European example, but it's true worldwide. they're putting tags on the cows in Europe, and for that, the reason is they want to know where they are, they want to have full tracking capability. And as you look at this, again, a very simple sensor, and you look at the amount of information it's generating, it's on the order of 200 megabytes per cow per year. Okay, well that's not that much, but we've got 1.5 billion cows. Now you start to add it up, and as you do the math, you're, 300,000 gigabytes of data, and of course there's more of the world than just cows. So what happens is all the stuff gets sent upstream because we're not filtering it yet. And so the bytes turn into megabytes, into terabytes, and on the recent reports now they're talking about zettabytes, which I believe is 10 to the 21st power. So not only are we being literally deluged in sensors, so billions and tens of billions of sensors are coming, and they're communicating more and more, not just to each other, but to the internet, we have to get thoughtful and smart about what we decide to transmit up into the network. We can't send everything. Sorry, let's go back again. Okay, so now let's talk a little bit about security. So sensors have changed the world, and beyond ways we can think about. But now we've got all these sensors surrounding us. What about security? What about privacy? Well, probably people have read about the famous Target breach. HVAC, air conditioning system was breached. Obviously, that's an enterprise example, but it falls back to a thread that fits into the home also. So in this case, the HVAC system was compromised, and there's a long story about how that happened. Got into the POS system, and then got into basically credit card information that was sent out over the internet. And this was a pretty big deal. Hundreds of millions of dollars were lost in this example. So let's look at the home now. You go inside the home. What are some of the similar kinds of things that could be happening? All right, so smart refrigerators now are sending spam, it appears. That's not the biggest problem in the world, but what if these smart refrigerators are also ordering food for us as they get more intelligent, and Google Express is starting to deliver food to our doorstep, and it wouldn't be quite as funny if all of a sudden some hacker got in and ordered 1,000 gallons of milk delivered to our doorstep. So as we get smarter, as these sensors do more for us, as things get more automated, the cost of security and in some cases privacy or loss thereof becomes larger and larger. Okay? And now maybe a more personal example from Kids Room. So we've also read about hackers coming in through the webcams, the baby cam and such. So there was one recent example with a 10-month-old where the parents heard someone yelling at their kid from the other room. And so they're listening to this, and they eventually go into the baby's room to see what's going on, and through the cam there's a voice basically yelling to the baby to wake up. And the cam turns as they enter the room and sees them and starts yelling, various obscenities at them. So again, kind of a strange example, but very personal now. The webcams are empowering. We can now watch the baby from other rooms. We can be traveling for business and be able to sort of look in and see what's happening. But the cost associated now with somebody hacking into the system has gone way up in terms of our personal privacy. Okay? So what do we do about that? So we'll jump a little bit into a concept called virtualization. And really what virtualization does is it creates buckets, in essence sort of hardware buckets in this example, to separate OSs and users from each other. And so to the right is a pretty standard example where you've got sort of two buckets. You've got a non-secure and a secure bucket. And on the secure side, you've got a bunch of applications that are mission critical, Netflix, Visa, etc. And on the left side, which is the imagination approach, you've got more of these buckets, as it were. In this example, we'll show there in a minute, perhaps up to even 8 sets of buckets. And so why does this matter? Well, from a reliability point of view, you can have one of the applications, in this case Widevine, has a problem. It gets hacked, it goes down. And eventually it comes back up. But while all this is happening, the other applications are continuing to run. So Netflix, Visa, as well as Android are unaffected. Now, if I have them all together in the same bucket, obviously you can imagine it shuts down other secure applications at the same time. And depending on what you're doing, that might be quite unacceptable. And then there's an efficiency power argument. each application requires, in this lower left example, a different number of microprocessors running. Android might be doing video encoding and for whatever reason needs 4 processors to be running at the same time. Widevine in this example, if you can see, only needs 2 processors to optimize the performance power footprint. And again, if you look at sort of other examples where you have only 2 buckets, it's much less flexible because all these applications have to use the same sort of performance, power performance envelope. So we'll talk more about this, but I think the message to take away here is virtualization relative to security is one of the important facets it takes to solve these problems we're talking about. It can't do it by itself, but it's one of the pieces. And as you start to add virtualization into your systems, and we'll bring this back into smart sensors here in a moment, more zones, multiple zone virtualization is much more powerful. And if you can afford it, that's the way to go. And if you look at another view of this now, on top of virtualization, you need security. They go hand in hand. And you need both to build really secure platforms. And so security is things like secure boot. You need a trusted environment where you can put these applications and run them on it so that people cannot easily hack in. And even if they do hack in now, you've got hardware virtualization that separates the connectivity piece from some of the mission critical applications that you don't want to have compromised. So they go hand in hand. Secure updates, secure data path, all those kinds of things will run over this trusted execution environment. And you may need different levels of security. In our products we'll talk about in a minute, we'll give you up to 8 levels of security in this one application. The parent from the child, from the service provider, you might have very different levels of needs and security capabilities that you want to allow them to have. Okay. And now let's look at, let's circle back and look at the sensor. So what are these sensors? It's really some sort of a processing element with some sort of a connectivity capability. And of course, there's sensors on the front end, it's a control output. So these are quite simple, and as we said, highly integrated going forward. And if you look at how this works now, we've got a very tiny microcontroller on the bottom. In this case, it's a MIPS M5100 or 5150. And by tiny, I mean 50 to 100,000 gates for those of people in the audience that are silicon people. So you can take now very high performance hardware virtualization, multi-level as it were, multi-bucket capabilities, and put it in a very tiny microcontroller that's appropriate to these sensors, these sensor elements. And you can see obviously visually here now, my applications running on OS 1 are separated, literally walled off from the applications running on OS 2 or some other application running bare metal. So if one gets compromised, others are not. In this case, up to 8 zones. And this shows the imagination IP. So we build the IP now. Again, we supply the IP to our partners, the semiconductor manufacturers, for the integration into the SoCs. In this case, we build the microcontroller with virtualization, as well as the radio processing unit, which does Wi-Fi and Bluetooth, including RF capabilities. Okay, a little more on the processor, without going back through all the capabilities. In addition to hardware virtualization, the MIPS products, as you might imagine, have the best performance efficiency, and we can show lots of graphs and curves against leading manufacturers. The other thing that's interesting is we've now built tamper resistance into the product. So there's little tricks that can be done where you can insert pipeline stalls and do other things that randomize data. One of the ways people get information out of these little processors is they'll look at the RAMs and they can measure based on energy 1s and 0s, as amazing as that sounds. So there's lots of tricks you can do to make it much more tamper resistant. From basic capabilities where if they open the box and they break a circuit, all the RAM is set to 0s, to other things that are a little more intelligent where again you can randomize data itself into the RAM, or you can add pipeline stalls into the processor, which allow it to keep people from measuring and knowing what your information is. And again, this is all being done in these little tiny, extremely low-cost microcontrollers appropriate to sensor nodes that we've been talking about. There's another use case I'd like to bring up where hardware virtualization becomes quite useful and I would say even important. As the SoC manufacturer, the silicon manufacturer brings out a product, there's quite a bit of software involved, not just in initialization, but in the functionality of the SoC. And as he sells it to the system integrator, now they're writing their own software and putting it on top. And not surprisingly, that system is sold to an ISP or a third party that puts more software on it. And through hardware virtualization now, what you can do is you can separate, literally separate, those memory elements from each other. Because the last thing you want to do is you build a product and find out the person you sold it to stepped on the memory footprint and caused QA problems you have to go back and fix. So there are other technical, I would call development, as well as perhaps protecting proprietary information reasons why you'd want to have this kind of virtualization built into your products. And then obviously, the sensor has to communicate out. So not only do you need to have smarter capabilities through security and hand in hand with hardware virtualization, but you also want to have end-to-end security out into the network. And we actually have a product called FlowCloud. And what FlowCloud does is, and this is software now, not hardware, what FlowCloud does is it's a platform that allows you to build on a defined set of APIs. So there's a number of services that are part of this, and I'll show one or two more slides on this, that give you the capability of having device-to-device or device-to-cloud, end-to-end secure communication. And you can see some of the details here. So there's core services, including authentication, authorization, registration. There's data services, payment services, and device-related services. So it's a very robust set of APIs that allows someone who needs to communicate to the cloud to very quickly and efficiently bring up products. And this is being deployed today. So this is actually a real product today that we're out selling. And a little more details on security. I won't drill into all of these, but security must be different and capable at different network levels. So what the application layer needs and what the network layer needs are quite different. And we handle all those pieces along the way here to make sure you've got robust and complete end-to-end security. Additional things like throttling, denial of service, all those kinds of sort of higher level capabilities are built in. Okay. So just a couple slides on imagination. For those of you who don't know the company, we're something on the order of 1,600 employees worldwide, public company out of the United Kingdom, out of the UK. Headquarters is just north of London near Heathrow Airport. About 250 million of revenue, global operations. With the acquisition of MIPS technologies, CPU technologies, we have a large presence now in the Valley on the order of 300 people. Also a very large technical team in India, as well as China. And of course, on the corporate side, a large team in the UK. In terms of IP leadership, number 3 worldwide in terms of products that we sell. And number one in GPUs with a very large percent of the market. Number one in video, encode, decode, H.264, H.265, HEVC, etc. Sadly, number 2 in microprocessors. There's another fellow that's larger than us. But we're shipping on the order of 700 million devices per year and growing consistently. Additionally, number 1 in connectivity, so Wi-Fi, Bluetooth, IP. So it's a very exciting time, and we do have, we believe, the broadest product offering in the industry by far. And to give you another sense of just scope for the company, we've shipped in something more than 7 billion products and about 3 million products per day. And this is my last slide. So, IoT is taking us on a path that none of us know where we're going yet. And what I would say to you is, it's hard to imagine all the places it'll take us. From the obvious things like, my front door no longer needs a key to open. Can you imagine kids 10, 20 years from now trying to explain to them how I carry keys in my pocket to go into a lock to turn the door, and the door camera didn't automatically sense me and authenticate me and open. It'll be impossible to explain why those kinds of things occur. Garage doors opening automatically. Those are the easy ones. The other piece that I personally am interested in is this whole idea of a super personal assistant. You're driving on your way to the office, it knows your calendar, it knows what's going on, your boss has just pushed the meeting out 30 minutes, and it tells you on the fly here, you've got 20 extra minutes at least to go get some coffee at your favorite coffee shop on the way to work. Or another one that I get 20 to 25 emails overnight, it might alert me as I'm waking up, getting out of the shower, getting dressed, it might alert me before I get in the car and drive that there's one email from the CEO that I probably should know the contents of. It gives me the key pieces and make a decision whether to call him before I get in the car. So all these kinds of things are coming, and those are the obvious ones. You know, there will be things in the next 10, 15 years that we can't possibly imagine. So this is a very exciting time, I think, for all of us in the tech industry, and we at Imagination believe IoT will be a major game changer opportunity for companies that own microprocessor IP and own connectivity IP and understand how to do device-to-device communication. Those are the people we think have a chance of winning big here. So we think this is a really big opportunity for us. And again, thank you for having us join you today.